Hey guys, what's up? My name is Gabe and this is Games with Gabe. This is the next episode in the Coding a Physics Engine in Java series. And in this episode, what we're going to be doing is just going over some basic math. So we're going to be going over just some vector math and some things you should be familiar with and things that you should be able to intuit very easily. Now, if you already know vector math, that's fine, but you just have to make sure that you know how to visualize what happens when you do two operations on two vectors visually, as well as knowing what happens mathematically. So yeah, let's check out the math that you need to know. Okay, so vector math. What is it? How does it work? Well, let's get started with notation. So if I ever have a vector A, I'm going to denote it as a capital letter, most likely with a little line above it that indicates vector. Next, I'm also going to have it in either angle brackets with like an x comma y notation, comma z if it's 3D vector, or I'll do parentheses, or I will do a matrix form. The matrix form is particularly useful if you're multiplying a matrix by a vector, because then you can think of it as just another matrix. Now, what does this mean though? So if we have a vector A, which is x comma y, that means you go right x and you go up y. You would plot a point there, and that is your vector. So you would draw the tail, which is this back part, to the head, which is this front part, and this is now vector A. So a vector, defined a little bit more mathematically, is literally just a line segment with a direction. That's all it is. And this is very useful for us, especially in physics, because you can use line segments with directions to denote how to move forward a specific direction. So if your character is moving forwards at this direction, we can add this vector to his position and he will actually move up to here. Now that brings me to the next part of vector math, which is addition. So if you have two vectors, A and B, how do you add them together? It's actually really simple. It's literally just AX, AY plus BX, BY, so vector A plus B, and it looks like this. Now, I'm never good with just algebraic expressions, so it makes a lot more sense to me just to say, if we have vector 1, 5, or 3, plus vector 2, 7, this just equals, you add the x's, 1 plus 2 is 3, 3 plus 7 is 10, add the y's, 310. It's really not that difficult, and vector subtraction works the same way. If you were doing 1, 3 minus 2, 7, you would just do 1 minus 2, negative 1, and you would do 3 minus 7, which is just negative 4. Okay, so nothing too complicated there, just add the x's, add the y's. What does it look like visually though? If you have vector A here, and you have vector B here, if I want to add those together, what does that look like? Well, you can think of it as picking up B, placing B's tail to A's head, and then drawing a new vector that goes between these two vectors, and that is your resultant vector. Or you can think of it as putting B's tail on A's head, and then this point up here will be your result, that point. It's good to think of it in terms of points and vectors because we will need both of those at different times. What about subtraction? So if you have A minus B, well then you would, first of all, pick up B. Once again, you can just think of this as, let's think of this as addition of a negative. So basically what you would do first is to make B negative, you would flip the direction. Okay, now B is negative. Then you would just put B onto A's head because you're just adding again. It's just adding a negative. So it would look like that. And then you would draw a line from here to here. And then that would be your resultant. So subtraction, very similar. Now let's talk about scalar multiplication. So with vectors, there's a lot of different types of multiplication actually, not just one. So the first one we're going to talk about is scalar multiplication. A scalar is any number, just a number. It's not a vector. And a vector is components, right? It has an x, a y, and a z, and a w, and whatever else. So we think of scalars as just like 1, 2, 3, 4, any sort of number. Multiply it, you just do 1, 5 times, and I'm going to use scalar multiplication with a star to denote that. We'll say like times 7 equals, you would do 7 times 1, which is 7, and 7 times 5, which is 35. So you do 7 comma 35. And that would be your resultant vector. Now, what does this represent? Once again, say you have some vector A, and you multiply this by a number greater than 1. So you multiply it by, say, 2. If you multiply this by 2, what you're doing is you're lengthening that vector double, right? Okay. And if you are multiplying it by something smaller, say 0.5, you are halving the size of the vector. It retains its direction, it just changes size, the length. So you can think of scalar means you're scaling your vector. And that is what a scalar multiplication does. Also very useful for things, for many different things. Okay, component product. Component product is not very useful, actually. I don't know any times that I've actually ever really used this, but we'll go over it just because it's something you would think of when you think of multiplying two vectors. Say you have 5, 4 times 3, 7, and you want to multiply these together. The most common thing you would think is multiply the x's, that's 5 times 3 is 15. Multiply the y's, that's 4 times 7 is 28. But it's not useful to us anyway. If you were to think about this graphically, what does this mean? If you have vector A and you want to component product with vector B, what this means is you're scaling it this much x and you're scaling it this much y. So then you would end up getting something like this, which just doesn't make sense, right? There's no way that this helps us when we're doing our math. If you guys know of any way that you use the component product for like real life things and stuff and using it graphically, let me know because I'd be interested. But I've never found use for this. I just figured I'd mention it because what I thought when I first saw this was, oh, you would just multiply x's, multiply y's. But no, that's not actually what you do. Dot product. So the dot product is actually something that is very useful. And it is not intuitive at all as to how you would do this. So I actually got my colors wrong up here, but this should be red, this should be blue. Okay, but dot product basically works as if you have two vectors, you add them together and you get a scalar number. This is just a number in the end. It's not a vector. So that's also important to remember. What is this though? So if you have ax, ay dot bx, by, we have one, I'm going to use 2. 4, we'll say dot, I'll represent that with a dot, 3, 5. What do? You do 2 times 3, which is 6, so you multiply the x's plus, and then you multiply the next one, which is 4 times 5 is 20, whoops, not parenthesis, equals, and then that would be 26. So this would be your result. And if you had more components, say it was x, y, z, w, you would just multiply the y's, add, multiply w's, add, and continue down the chain. So it's not too hard to remember, but it may not be apparent at first what this means. There's a relationship though. So say you have vector A here, and we'll draw vector B like this. The dot product has a direct relationship to the angle theta between the two vectors. Now, I say relationship because it's not, this is not the angle. It's related to the angle. So we can intuit things about the angle based on the dot product value. And we can actually get the direct angle from the dot product value. We'll go over how to do that in just a minute too. But next up, we have the cross product. Now, in 2 dimensions, there is not really a thing as a cross product. This is actually more commonly known as a wedge product, or I've heard perp product for 2D vectors, but it's not a thing. In 3 dimensions though, we'll talk about what it means in 3 dimensions, and then we'll explain why it's useful to us in 2 dimensions. So if we had 3 dimensions, we'll just do an example like that. We had 3, 4, 5 cross 1, 2, 3. So say we had 2 3-dimensional vectors like this, and we want to cross them. What you would do is you would do I, J, K, which is also just X, Y, Z. It's just the vector notations for those. And then we would say 3, 4, 5, and then we would say 1, 2, 3. And the way that you would calculate the cross product, I actually haven't done this in a while, so I'm not sure if I'm doing this right, but let's see, we would do for the X component, you would draw a line out here, so then you would cross these two. So you do 4 times 3, which is 12, minus 5 times 2, which is 10. For the Y, what you would do is, and this is just the easiest way for me to remember how to do this, erase those lines. You would do cross it this way. So you would do 5 times 1, which is 5, minus, and then you would cross it this way, which is 3 times 3, which is 9. And then for z, you would go this way, 3 times 2, which is 6, minus, and then 4 times 1. So would be these two, which is 4, which gives you a vector. Switch back to black now. 2, -4, 2. Okay. And that's using right-handed coordinate system. I'm 90% sure I did that right. So what does this cross product represent? We get another vector, right? In 3 dimensions, what this represents is, say, vector A looked something like this on the x-plane. Vector Y looked something like this on the y-plane. Then what we're getting is a vector Z that looks like this, since we are in... Actually, the vector Z, I'm pretty sure would actually be pointing out that way, since we're in right-handed coordinate systems. But yeah, and so what you'll notice is that this vector Z is actually orthogonal or just perpendicular to x and y. So you can think of that, it's right angles to both of these. And so when you cross 2 vectors in 3 dimensions, what you're getting is a vector that is right angle in the 3rd dimension. Now, 2-dimensional vector products or wedge products are a lot easier. You can just do this times this minus this times this, which is just axby minus aybx. But what this represents in 2 dimensions is actually kind of unclear. We will end up using this in some angular velocity equations where you would normally use a cross product for 3 dimensions. This works pretty good. And what I like to think of it is you can think of it as if it has a 0 z. And so we're sort of getting something in the z dimension is almost what this value represents, is some angle in the z dimension that these 2 vectors are related at. So yeah, no good way. We'll take that when we get to it, but for now, just think of it if you cross them using some math library, what you're getting is a perpendicular vector in 3 dimensions. Okay, something a little bit easier, vector length. How do you determine what the length of a vector is? Say you have some vector A, it's like this. Well, how long is that vector? That's actually not too bad to figure out. So we know that vector A is represented by 2 terms, x, y. This is the x length, this is the y length, literally is what the vector stands for. Well, if I replace this with A, lowercase, and B, this starts to look like something. And I say that's C, and I draw a little right angle to determine that this is a right triangle. Well, we know by Pythagoras' theorem that c squared equals a squared plus b squared, or a squared plus b squared equals c squared, which implies that c is the square root of a squared plus b squared. So yeah, and since length is always positive, you don't have to worry about plus or minus. We don't care about that. This is a length. So we know that the length of A we can denote by a squared plus b squared. And so that's how you get the length of a vector. Now, couple more things. So unit vectors. All that means is we'll say a unit vector u is just a vector that has length 1. A vector that has length 1. This is very useful because you can use this to denote a direction. Okay? If I have this vector that's length 1 and say I want you to go 5 units in this direction, all you have to do is multiply this by the scalar number 5. It will extend the vector 5 units in that direction and give me a point in space. This is where you would end up. Okay? So this is very, very useful. You use this in AI and pathfinding and player raycasting and everything to figure out how far you need to go. And you can just say, hey, I have a direction which is represented by this unit vector. Just go 10 units that way. And then it'll go 10 units that way. So it's easier to say go that way than it is to say go 5 left and then 6y and then 7z. So this is just easier way. How do you get the normal or the unit vector though? So this is something called the normalization. This is probably not a very good term because normal means something else. But the normalization of a vector is getting the unit vector, turning it into a unit vector. So say we have some vector A that is not a unit vector. Say its length, I am drawing horribly. Say its length look like this, and we have length of 3 for the x and length of 4 for the y. Now, what we would find out is that if we took the magnitude of this vector, which I will also denote which is a single absolute value bar. So the magnitude or the length of the vector, that's all the same thing too. So the magnitude of the vector is just the square root of 3 squared plus 4 squared, right? Because we have 3, 4, which is just the square root of 3 squared is 9, 4 squared is 16, 25, which is just 5. So A has a length of 5. That's not 1. We want to turn it into a unit vector though. So we want to retain the direction, but shrink it down. So that's just 1 in that direction. How do we do that? Well, that should be an equals. The normal of A is just A over its length. So if we just say A over the length of A, well, we know that A is just 3, 4. We know that the length of A is just 5. So what we would do is we would just say, well, then A is 3/5, 4/5. And now A is a unit vector. This is now of length 1. And we can confirm that because if we do 3 squared over 5 squared plus 4 squared over 5 squared, which is just the length, we would get 9 squared, which is 81 over 25. Or no, we would get 9, not 9 squared. 3 squared is 9 over 25 plus 4 squared is 16 over 25, which is 25 over 25, which is 1. So we can confirm that this works every time, and it makes sense if you think about it, because if we divide by the length, what we're doing is in essence making it so that when we do square this next time, it will be length 1, and that's a u. So that's unit vectors. Very important, very useful for lots of things. Last thing I will talk about is the dot product and its relationship to the angle, right? So I said it has a relationship, but how does it have a relationship? Well, we can formally denote it as A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between the vectors. Now, deriving this relationship is difficult. I'm not even going to attempt to do that, but you have to use some weird circle geometry type stuff. But we will talk about what this means for us. So what we're saying is if we have two vectors, A and B, the angle between them, we can write theta is equal to A dot B is equal to the magnitude of A times the magnitude of B times the cosine of that angle. In other words, we could also say that A dot B over, so if we divide this to this side, over their magnitudes is equal to the cosine of theta. Now, let's think about this for a minute. What happens if A and B are both unit vectors? If A and B are both of length 1, well then this does not matter, because if they are of length 1, then that is just 1 times 1, which is 1. Anything divided by 1 is itself. So then, if A and B are unit vectors, we get A dot B is equal to the cosine of theta. This gives us some important relationships that we can define, because now, without having to do anything fancy, we can say, hey, because cosine and sine, taking the cosine of something or taking the sine, or the inverse cosine or the inverse sine, is very expensive on the CPU, takes up a lot of CPU cycles. Taking a square root, which we do here, also takes up a lot of CPU cycles. But we can actually get around that too, and we'll talk about that in the future and stuff. But anyways, so A dot B is equal to the cosine of theta, right? What this means is that if A dot B equals 0, or no, I'm sorry, if A dot B equals 1, right, then that implies that theta is 0, which implies that the vectors are parallel. It does not look like it, but believe me here, they are parallel, which means that these two vectors will never collide. So A dot B equals 1, they are parallel. What about if A dot B equals 0? Well, we know that the cosine of 90 degrees is 0, cosine of pi over 2 is 0. So that means the two vectors are parallel. I mean, perpendicular, right? So they are at right angles to each other. This is also very important. So what can we intuit? We can intuit that if two vectors have the dot product equal to 1 and they are normal vectors, they are normalized, then we know that they're parallel. But if their dot product is 0, we know that they are perpendicular. And what that means is that anything between 0 and 1, so if their dot product is between 0 and 1, it will give us an interpolated range between 0 and 90 degrees. It will end up looking like something between there. It won't be exactly, but it will give us something in a normalized range of 0 to 90 degrees. This is important for like lighting calculations and stuff. If you're doing rendering, you would be using this. And so we may take a look at that too once we get into 3D and how to do 3D lighting and stuff. But it's also important for us in physics because knowing whether two vectors are perpendicular or if they're parallel is also very important to tell whether they will ever collide or not. Okay, so this has sort of been a little intro on the vector math. If anything doesn't make sense, please leave a comment and we can go into it a little bit deeper when we start to talk about these topics and how they apply. But I really wanted you to know how they are explained visually. If we're ever going over something and you can't remember how it is visually and I don't explain it, go back to this video because it's so important that you understand what is happening on your screen visually and how it relates to the math that we're going to be doing, because physics uses a lot of math and that math always has a relationship to how it's actually behaving in the real world. Okay? But that's it for this video. I hope you guys enjoyed it. If you did, please hit like and subscribe, and I promise we will start coding in the next tutorial, in which we will start coding our primitives so that we have a library which we can start pulling from to do some physics with some primitives. All right, guys, I'll see you then. Thanks.